we've done a lot now with fluids. This next one, this is going to look like the most daunting equation that we come across in really all of the Physics 1, Physics 2 sequence. It's not so bad, but I'm going to write it out first. It says this. Most of the problems that we actually do with this won't use the entire equation. They'll just use little parts of it. But it's good to be able to see where this comes from, and it's good to be able to use the equation in its entirety too. So where this comes from, this might look some kind of familiar. If we take this entire equation and multiply through by an area, if we take this entire equation and multiply through by volume, we get something that looks a little different. Pressure is force over area, so this is an F1 over an A, and then multiplying that through by volume. Volume is an area times a distance. So this would be times an area times a distance. Area and area drop, and I get an F1 times a distance. Next one. Density. Density is mass over volume. So if I multiply that through by volume, I just get mass. So this is going to be an mgh1. Same thing here. I'm going to get a half mv1 squared equals same thing on the other side. This thing looks like work. This would be potential energy from gravity. This would be kinetic energy. Bernoulli's equation really does look an awful lot like conservation of energy. It is just an energy per unit volume all the way through. So that's the first part on why this shouldn't look as awful as it does, maybe, or shouldn't feel as awful as it looks. But now let's see what kinds of situations this goes to. Okay, I have a pipe like this, and I have something right here that measures pressure maybe. I'm going to have a fluid flowing through here. And maybe I want to know what my pressure reads up here. So I'm going to need some values. First, an area. Let's have our area 1 here be 1/10 of a square meter. Let's have our area 2 up here be, I don't know, half of that. We're going to need a height difference because we have one. So if that's an area of 0.1 square meters, maybe this is a height difference of, let's go 2 meters. I know it's not exactly to scale, but we'll be okay. And our fluid over here on the left side is going to be moving at, I don't know, 4 meters per second. I would like to know the pressure over on the right side. First, I'm going to use my flow rate equation. My flow rate equation says area 1 times V1 equals area 2 times V2, and that's going to let me find the speed up here. So I'm going to say V2 is A1V1 over A2. So A1.1 square meters times 4 meters per second over V2, which was 0.05 square meters. This thing comes out to be 8 meters per second. Now I have V2. Once I've got that, now I'm going to start plugging into this thing. Up at the end here, I would like to have atmospheric pressure. So I'm going to go with 101 kilopascals here. I need to know what's my pressure down here going to be. So this is an absolute pressure, this 101 kilopascals. This is maybe opening out to open air somewhere. What I need is to find my P1. So I'm going to make that be red. Pressure 1 is going to be pressure 2 plus rho GH2 plus half rho V2 squared minus half rho V1 squared. And when I plug in all those values, I get 145 kilopascals here. So I'm able to get my pressure reading down here based on my pressure reading up here and how the water inside the tube is flowing. I get 145 kilopascals. It's a higher number, and that makes sense. It's going to be more pressurized here to push this up and to an exiting pressure of 101 kilopascals. Now, the big way that I'm going to use Bernoulli's equation isn't actually this, but if I see a closed pipe and see this whole setup, it's a specific type of question, and you can kind of see it coming. The big ways that I'm going to use Bernoulli's equation are in trends. My equation looks like this. I'm going to make a couple of statements. If I'm working at a constant depth, and this is really the big one, then this value will drop with this value. And I'm saying pressure plus half rho V squared equals pressure plus half rho V squared. What that means, if I have a speed here, a speed of fluid that's higher versus a lower speed here, then that means the lower speed is going to have to give me a higher pressure. The higher speed is going to have to give me a lower pressure. So this is what happens with a couple of different things that will look really familiar to you. When you have a person on a motorcycle, there's always that interesting thing that happens that the back of their shirt seems to flap up, and you kind of wonder, like, why would it? And the air is flowing right over it. Shouldn't that hold it down? But we can kind of see what's going on. So as they are riding on this motorcycle, we see a lot of the time their shirt tries to flap up. We've got air that is passing over them, and underneath their shirt there is not really much airflow. Over here we've got a relatively high speed air, but what that means is that we get a pressure differential. They just lost part of their motorcycle. We get a pressure differential. Over the back of their shirt, they get a low pressure, so they get a high speed, so they get a low pressure. Under, they get a lower speed of air, so they get a higher pressure. That force differential makes this pop up. This comes up in other cases too. The big one that we see this used in is airplane wings. When we have an airplane wing from a side view, it looks something like this. and then we get airflow. Now, as the wing moves through the air, we've got these air particles. We get airflow this way. We get airflow this way. And because the air isn't really what's moving, it's the plane moving through it, we still get the relative motion, but that means that these paths, this particle and this particle, as the air cut through it, are going to end up still being somewhere near each other potentially. So this top particle travels a longer distance. The bottom particle travels a shorter distance, and they do this in the same amount of time. If this top one travels a greater distance, that means it's got a greater speed. Bottom one's lower distance, lower speed. Now we look at pressure. Higher speed means we get some pressure. Pushing down on this wing. Lower speed means we get a higher pressure. We get more pressure on the bottom of this wing than we do on the top, so we get an overall lift force. Now this isn't, of course, the only thing that keeps an airplane in the air. A big part of what helps is that this airfoil is actually angled. Not only do we get the lift from the pressure differential, we actually get something that points backwards a little bit. I will do a separate video on lift and on the dynamics of airplane wings, but as this air travels over, we get a couple of different things, one of which is that this is also pushing against the wing. If it pushes against the wing and the wing is angled, that means we have some component of this that's pushing into the wing and helping to lift it up. So I'll do a separate video on that. For right now, what we need is a couple of things. One, if we start with a convoluted looking very specific problem, we might be looking at a full Bernoulli equation. Two, higher speed equals lower pressure. That's the big take-home message.